In this problem, we are going to count the number of rectangles in this weird figure. Okay, this is obviously a counting problem. Before we dive into this problem, I want to give some advice to all students who are studying the counting techniques. In almost all counting problems, especially the counting problems in the exams or the contests, you want to categorize your problem or doing casework so as to split your problem into smaller scenarios or into cases that are easier to handle. All right, that's a general advice. So let's look at this problem. In this problem, we are going to count the number of rectangles. So obviously we see a lot of rectangles, rectangles here, rectangles here, right? A lot of rectangles. But on the other hand, we also recognize that this shape is kind of weird because we see a lot of problems like this when we have the grids. And then we count the number of either rectangles or squares. Let's say rectangles in the grids. So something different between these two figures are that each rectangle in the grids can be subdivided into pieces such that each piece is a rectangle. However, in our problem, some of the rectangles are not sliced properly. Or, for example, let's look at this one. Let's look at this square. So it's a rectangle, right? So in this rectangle, it's not sliced properly. For example, this line is not cutting through this rectangle. So it's not really cutting this rectangle into smaller rectangles, right? It's just like cut out a rectangle, right? It's just like cutting out one piece from the larger rectangle. So the techniques to thoroughly count the number of rectangles without double counting and without missing any of the rectangles will be different or somehow hard in this problem. Okay, let's remove the messy lines and do the extra work. So in this problem, we want to do the casework and find different categories of rectangles so that are easier to handle. So for example, let's call the first category the big or whole rectangles. For example, this is a big rectangle. We call that whole rectangle, which means that such rectangles are not part of some other even larger rectangles, right? So they're unique and they're easier to count. So let's call this whole rectangle. This is not like a formal terminology. I just name it, randomly so as we can properly subcategorize this problem. So let's call this whole rectangle. And we know that there are three, right? So this is a big rectangle here, and this is a big rectangle here, right? And this is big rectangle, right? So these three are easier to recognize. All right, let's look at the second one. So we always remember that diagram of grids, right? So these are always a good example so that each rectangle can be cut into smaller rectangles. So we want to find a similar pattern in our diagram. So are there rectangles or big or whole rectangles that we found in the first category that are cut through into pieces, either horizontally or vertically? All right, let's look at them one by one, right? We have three whole rectangles. So look at this square-like rectangle. Is there any lines cut through it vertically or horizontally? So this line is certainly not. This line not, this line not. Actually, there are no lines cutting through this rectangle so that we split it into pieces. Therefore, we have 0. Let's call this the second category. What should we call that? Let's call that grid-like rectangles. All right. So there are 0 smaller rectangles for the first whole rectangle, right? And then let's look at this piece. Are there any lines cut it through vertically or horizontally so that to split this rectangle into pieces? So certainly yes, there is one. Do we see this red line? This one cut through this rectangle horizontally so that it split this rectangle into pieces, into 2 pieces, the top and the bottom. Are there any lines that cut through this vertically? Like let's use green. Like this line? No, right? It's not cutting through. So we know that for the second whole rectangle, we have 2 grid rectangles. All right, so let's call this, we have 2 here. And then plus, let's look at the third whole rectangle. Are there any lines that cut through this whole rectangle vertically or horizontally? Yes, there is one. So look at this. Right? That line cut through this rectangle vertically so that we have this part and this part, right? So we have 2 grid-like rectangles. So we will add another 2 here. Okay, now we've considered all 3 whole rectangles. So we exhausted all grid-like rectangles already. So let's remove the red line. Let's remove those red lines, right? So we have 2 plus 2 equals to 4 grid-like rectangles. Okay, so now let's go even finer, find even smaller rectangles. So what kind of smaller rectangles can we consider? For this picture, we want to find the rectangles that was from one or more of the big whole rectangles. There are no lines cutting through. It's just a part of big rectangles. In that scenario, let's use, what should we use? Let's remove the lines a little bit, right? Let's remove the lines. Okay, and then let's still use the blue pen. So we know that this one, look at this one. So this is a corner of either the rectangle, let's call this 1, or rectangle 3. Let's call this 2. These big whole rectangles. So this is a corner of the big whole rectangle, right? So that is 1. So we call that, how do we call that? So we call that corners. All right, these are just some random names so that it will help us to subcategorize the problem. So that's a corner. And are there any other corners? So that's one corner. And any other corners? Is, for example, I'll use the red pen. Is this a corner? No. That's not a corner. That's a grid rectangle, right? That's belongs to categorize 2. That belongs to here. So this is not a corner, right? So only this is corner. So of course this is not a corner. That's a grid rectangle. All right, so how many corner rectangles do we have now? So all what I can find is 1, right? We only have 1 corner rectangle. That's all what we have. All right, then what else? Have we exhausted all the possible cases? Probably no. So for example, let's look at this one. or this one, right? So here's the deal. When we do the casework or subcategorize the counting problem, we may not be able to exhaust all the possible cases unless we know the answer already. Otherwise, we will find some subcases and we will do the casework. And while we do this, we may find new caseworks. We'll keep on adding to our list. For example, these ones are neither whole rectangle or grid rectangle or a corner rectangle, right? They're really small. They're not a corner. They're actually part of either the corner rectangle or grid rectangles. So in that scenario, I'll call this case casework 4. Let's call that small, right? I'll call that small. So they are small rectangles, meaning there are no smaller structures inside it. Then how many small rectangles do we have? As we pointed out that we have one here without any finer structures inside it, right? So we have another one here. And we have a third one here. So we have 3. So have we exhausted all the possible cases? I guess the answer is probably yes. So when you do such kind of problems, you have to re-examine your answer multiple times and to make sure that you didn't miss anything. All right. So this is all what we have. Now, let's count them. We have 3 here, 4 here, 1 here, and 3 here, right? So the total number of rectangles is 3 plus 4 plus 1 plus 3. So that is 5, and that is 6, and the 5 plus 6 equal to 11. So the answer is D. Now, I'm going to introduce a second method. And you may wonder, this problem is so hard. Why do we need to learn so many different methodologies? Especially for hard problems, you actually need a second or third methods even more than easier problems, because then you can double check if your previous answer is correct or not, right? So let's do it. So the second methodology is also very common, especially for these geometric related counting problems. For example, to count the number of certain shapes. So that is what we call that. So I don't know the formal name. So let's just call that by removing lines. What I mean by that is we started from some lines in this figure, and then count all the rectangles that has that line. For example, let's use this line. So I want to count all the rectangles that has this line, right? And once after that, we can remove that line. Then eventually by removing the lines, one by one or part by part, we can reduce this problem into easier cases. For example, let's look at this line. So how many rectangles are there that has the side of this line? So of course 1. We only have this big rectangle, right? There are no other rectangles with this line. All right. So let's remove that. So we have 1 here. I'll put a 1 here. Plus. So since we've already used this line, let's remove it. Since we removed that line, we also remove this part of the line, right? Because otherwise, the top is open. There's no other rectangles that can use this part of the line, right? We got to remove that. So it's very safe to remove that line and also remove this line, right? Okay, then what's left is an easier problem to handle. So let's keep on doing this. Then what's next? Let's look at this line. All right. So for this line, how many rectangles that have this line as a side? So we know this is one of it, and then this is one of it. 2, Beautiful. So let's remove these. Okay, I'll put 2 here, and then it's safe to remove that line. And for the same reason, the bottom is open, so it's safe to remove these lines, these segments, and then remove this segment. Okay, so now let's look at this line. Remember, when we use this technology, we always start from the outside or start from the easier lines or easier line segments. So this line segment is easier, right? Then how many rectangles have this line segment as a side? Then we have that, and we have that. Still 2. Beautiful. So let's remove the lines. Okay, so we still have 2 for this line. So let's remove that. And for the same reason, since the left-hand side is open, let's remove these open line segments. Beautiful. Now you can see that our figure is much easier. So now let's redraw this. So what's left is this. All right, and what else? So this line goes a little bit further, and we have that, and we have that. Beautiful. So that's what's left for now. Then what's next? Let's change color. Okay, let's use the blue color. So now an easier line will be this, right? So for that line, how many rectangles have that line segment as a side? So of course, only 1. So we plus 1. All right, we remove this line, and of course, it's safe. Oh, actually, our picture wasn't correct. It's this. All right, that's our current problem. So let's change back to blue. So since we moved this line, right? So this line can be removed. And the same for this line segment. And then for this line segment. Okay, so now what's left is even easier, right? It's just like this, what do we call that? It's like a 7 shape figure. It's like 7 here, right? Okay. So now let's, which line is easier? This line. Is this line easier? That line is easier, right? So we have a rectangle of this and a rectangle all the way to here. These 2 rectangles have this line segment as a side. So we need to plus 2. Then we can remove this line and remove these lines. Right? So now what do we have? We only have this shape. Is that right? Okay, this shape is much easier than we thought. So how many rectangles do we have in this easy shape? 3, right? So it's 3. Okay, so now do we still get 11 for this kind of counting technique? Let's see. We have 5 here. We have 6 here. Beautiful. 5 plus 6, that's 11. So we double confirmed that D is our answer. If you like this video, please subscribe and thumb up. If you have questions, please comment.